I log into LinkedIn and do a post through my laptop, and then suddenly I move on to my mobile app, right, to see that post. So there would be a replication lag, and how do you mitigate those replication lag? How does the system knows that? Okay, because I may see a different data. I would have posted it, then I would think that the post never went through it. Then I may do a repost, and we could end up with duplicates, right? How systems are trying to rectify that?
Sure, sure. Go ahead. We can start now. Awesome.
Yeah. So this is more about from the following class. It's a problem with the replication lag. So previously we saw the implementation of replication log, how we implemented. There are 4 different ways that we implemented replication logs. So this is a follow-up class with that. We see problems with the replication lag. So before moving on, what are the problems? So I'll just state what is replication. So replication is nothing but keeping the same data copy across different servers, basically. So the node that has a copy of the data is called replica. 1 minute. I think. Yeah. So the node. So when you have replicas, right? So you can do a fault tolerance, because when there is a faulty node, but you can still read data from the other. From the other replicas, which makes it more convenient, and the downtime is reduced, basically. And you can spread the loads across different replicas. You can say that if it is a read heavy system, you can basically spread the load across different replicas of having the same copy of the data. The other point is that static data are very easy to do replicas. Say, for example, your configuration, right? Say one of the node goes down, but copying a configuration data, which is actually a static data, to a different host, and then restarting that host is very easy, and it can be replicated. So if there is a change to one of the data, then it can be easily replicated. But the problem comes with dynamic data that frequently changes. So that is where the complexity of replication actually comes into play.
Yeah, Manoj, your sharing is now blank. Just see if
Okay,
your
1 minute.
device might have got into.
You reshare it?
Yeah, maybe it got in sleep mode, so then the
Yeah,
sharing.
I think anything. So before distributed systems, right? Even before distributed systems became very popular. Something called RAD was used. It's nothing but a redundant array of independent disk was used. So nothing but it is a single controller where each of the nodes are very independent. Say that you have A block here, then you have A2 block here, A3 and A4. So if the live data is flowing here, and so if say that this block goes down, then immediately it goes and starts looking into the A2 block. So that is how the data redundancy was created. So one single rack where you have B1, C1 and D1. So every rack will have its own data replica of the same disk block. So that to reduce your failure of the system. So that's how it was. Yeah, normally that's how it's been done. And even before distributed system become very famous, this was something that was used. And so nodes can be, so all these nodes, right, can be distributed geographically to different locations to have your data safe, and it can be for these, right, normally all the reads goes to one location, but it can be replicated and kept. If there is any problem, then you can switch over to the different disks. So that's how it was really maintained. So now let's look into the problems with replication lag. So one thing is that so the leader-based replication, right, requires all the writes to go to one node. but the read always goes to different replicas. So that's one thing that normally is right. All your reads goes to one. So basically, it goes directly to the reader. To the leader, where all your writes happen, and the replication happens after that. But all your reads go to different replicas, so that you can. So the problem here is that say that you made a change in your profile, and what happens that then you subsequently try to see that the changes got affected, and suddenly what happens, it goes to a different follower or replica, but you do not see the change. So that's what is called actually a replication lag. So you're seeing two different events, but you have done something, but you don't see that event immediately. So that's because the replication lag is taking place between two different systems. So how do you solve that? That is what we are going to speak about it. So so the other point is that you can create many followers and distribute the reads across these followers. This removes the load from the leader and allows the read to go through the replicas. So basically, you can have n number of replicas. So in a read scalable system, right, normally that's what you do. So what you do is, you basically, when there is a very minimal writes, then say for Twitter, right, it's actually a read heavy system when compared to writes. So they'll have a lot of followers created, and you basically, all the read requests would be sent across different replicas or followers to read that. That is where normally, how does Twitter handles that? All these, right? The fundamental still remains the same. How they are trying to handle that. That we'll be speaking. So one thing is, any scalable architecture, right? Any read scaling architecture, right, is normally done through synchronization. But synchronization has its own problems, like say that one of the node goes down, or if there is a network breaker, then the entire data, so the replication, you'll see inconsistency across all the readers who are trying to read that data. And so how do you mitigate that? So that is, again, you use asynchronous, but asynchronous has its own problems. The other problem is that asynchronous, right, will have data inconsistency. You'll be some of the followers would lag behind some other followers or leaders, and that is where you see data inconsistency. So what you do for that is to stop the writes, and until the followers catch up the leader, you do not allow the writes, and that is how you call it as eventual consistency. That is how eventual consistency comes into play. So this is something that normally we need to know how replication lag can be mitigated initially. So the other point is that, keep in mind that you should keep it always in mind, is that eventual consistency or eventual right is a vague statement in a distributed system, because it has no defined timeline when the follower, sorry, 1 minute. Let me reshare it, or let me increase the time. So one problem is that it's not, so eventual consistency is that one problem is that you do not have a defined timeline that how long the replica can actually fall behind. So it's up to us to design what is eventual consistency. It has no defined timeline. So your MongoDB can tell different than another DB, which is actually eventual consistent. The times may be different, how it has been architecturally implemented. So yeah, we should know how much milliseconds it's going to lag, or how many seconds it is. That's very, very much, we as engineers, we have to look into that. So how do you solve all these is, one of the way is by read your own writes. That is to solve, say that as I told previously, you have a profile and you made a change to that profile. Now you try to read that profile, you see a different data coming out. So how do you solve that? That is read your own rights. So all the profile changes, right? It is recommended to go directly to the leader. So whenever something that the user has modified, and read it from the leader itself. You do not go to the follower. This requires that you have some way or knowing that whether something might have been modified without actually querying it. So for that's what that's what I told. Profile change is one of the best example that you know, because your client knows that you made a change to the profile, and you directly go to the leader always when you're trying to retrieve the profile. That solves the problem of this issue of replication lag, and you don't go to the follower. So other one is that upon 1 minute write and read from the leader. So one thing is negating the benefit of read scaling. You can track the time of the last update, and for 1 minute after the last update, then make all reads from the leader itself. So until 1 minute, you make all the reads from the leader itself, and then subsequently you move on to you within that 1 minute, you think that all the replicas have got the latest data, and then subsequent reads are sent to the replicas to read it. So other one is that client can remember the time of the last write and redirect the followers to all the changes till that time. So that is so say that the client, right? The client system has to know that any request that it comes needs to redirect it to the follower that has the latest updated value. So you do that. So one problem is that when you shift between two users, right, which I mentioned previously, that when I make some changes in the LinkedIn in the browser and then move on to the mobile app to see that. So how do I know? How does the system knows that? It's the same user who's trying to shift between two different devices. So because system cannot know that it's the same user, right? So one way is to mitigate is by storing metadata information in the system that it's the same user who's trying to access the data. Then you start directing it to the leader or to the latest replica, which has the latest data. So that's how you solve this problem. So this diagram, right, it gives you more of an understanding. I would share this document. So it says that video won't write. So here the write comes and then it writes into the leader and OK status is 10. And then the replication starts into the replication 1. Then what happens is by that time, if someone is trying to see my read, right? So that is when you do not see the data. So they will see the old data. And what happens that, so from here, right? So when they read into the replica 2, but if this request would have come in here, right? So if this would have been here and it would have read from this replica, it would have got the changed value. What happens is then, so after this timeline, after the response is sent back, then the insertion happens into the replica 2. So after any subsequent request after this, would be able to see the actual data change in the system. So that's how normally it happens. So this is like, so this is for this read profile from the leader. That's the diagram for this one. And read from the leader is basically you make sure that all the requests, right, goes only to the leader. So you have modified the change here, then subsequent request is redirected into the leader. That's why you see found data. Then after that, the replication is done here. Then what happens is, so basically what happens is, so you do when some other user profile gets changed, then that's how it follows the same pattern. So if someone has done, then send him to the leader itself to select the data. If not, then wait for it and then make sure that it goes to the follower that got replicated. So this diagram is more of giving and picture representation for each of these statements. So the last statement is like, yeah, so basically you do it from one of the device. Then what happens is you check the time. So if T3 request is greater than this one, then you see that the replication has happened in the replication one, then you send back the time. So then if T4 is coming, right, by the time there's an insertion happening here in the replication two, and if this time, right, if the insertion is actually happening and but the time is actually greater, then you still make the request to wait for it, wait for the insertion to happen and the replication to happen, and then you respond back with the value. So that's how you do when you have when a user switches between two different devices. But the point is that you still need to have metadata information stored, so that you know that the user who is coming to coming from a different device, the same user who is coming from a different device, no, the system knows that it's the same user who has made change from a different device. Any questions here? So the other point is that, yeah, so when it is actually distributed across geography, right, actually the complexity increases more. And the other point is I'd say that a leader request comes from a different geography to a leader, but that leader does not have a leader data, then it has to redirect it to a different data center to the leader itself. It should not redirect it to a follower or something, because the follower may be falling behind the leader itself. So yeah, so the complexity increases as you go beyond different when the data centers are put into different geographies.
Correct. So, Manoj, here I have a question.
Yeah.
So, you can have the database cluster with various server instances running in the same location. And
Yeah.
so, there also you need to replicate information accurately, because there could be some delay because of various integrity checks, and data write could be expensive operation.
Yeah,
Then,
so that's why we tell, right? So we normally put it into the leader,
yeah,
and so all the rights will always will go into the leader only. So that
right.
is where you maintain that this thing integrity of data. If say that request goes here and request goes here, right? Then it becomes very difficult to manage that. Then there will be a lot of stale data lying here and there. So that's why. So
Right.
now say that, yeah, so that's why we tell that read your own rights and read it from the leader itself. So that's why we tell that you have 1 minute time, or yeah, it's more of this 1 minute time is more of we defining it how replication has to be done. But to say that we think that it would happen within 1 minute of time, all the replication would be done. So then you tell that within that given point of 1 minute time, you always send the request only to the leader. After that certain 1 minute time, right, you start sending the other request to the respective replicas to avoid the stale data being viewed by the
Okay.
reader request.
Okay. Yeah, so that is one set of problems. Other set of problems, now many organizations have databases spread across different data centers across different geographies.
Yeah.
So there is different database instances, right?
Yeah, so for example, if you see into Yugabyte, one of the presentation which was given, right,
Yes.
and that they also speak about this replication lag across geography, where they tell that, say that a request comes, which has not get replicated, then what does that? So each of the instance, right, they have their own masters, master concept. It's a master concept within each of the nodes. And what does that? So the point is that all the masters across the geography should have the knowledge of which node is having the latest data for that user. So what happens is that master then redirects the request to that particular, say that it's across geography, then it sends to the other data center to the other master.
Okay.
So that's where then that is how it is. So now you see then there will be latencies obviously in distributed systems, right? Yeah, you need to somehow trade off this or that. So you need the latest data, then obviously you need to have little performance impact, because if it is going from one geography to another geography, then there's going to be a performance impact.
Yes.
So
And
now we have to design systems how, for which systems where we should route and which system we should not route the data, and we should respond back saying that the data is not found. Yeah, so that it depends on what type of application or what type of product you're trying to build, and what is the use case, and what is the problem statement that we are trying to solve. It all completely depends on the engineer or the product that we are trying to build. So it doesn't mean that every time you need to route and get the data from a different geography always. Yeah, it may be local data that you're looking at, and if it is not available here, then it's not going to be available across. So,
right.
yeah.
So yeah, these are the two scenarios. Then there is a third scenario also, where, say for example, I'll give, say you have product information in an e-commerce application, and in this there are different modules. One module is probably responsible for payment. So the
Yeah.
payment module should have the updated information of pricing, right? And at the same time, there could be a different set of database and fields, and there is a inventory management system where also you need the pricing, because for shipping items you need to put the price in the label. So
Yeah.
so if you have to keep such data values in sync, they are in different databases and even in different tables. So is the same considerations applicable in this scenario as well?
Uh, no, it depends, right? See, mostly, right, like inventory, or it's going to be like your your order systems, right? They're going to go always to the master database, because maintaining the inventory is very important. I just saw during this what I tell this Flipkart. There was a Flipkart sales, right?
Mm-hmm.
I can easily find out bugs in that because when I applied for something, right, I actually was trying to sell my older phone. I was trying to do an exchange. Okay, what happened is the the pricing, right? The pricing system was still not able to recognize my change. It was waiting for that change to happen, and that is when, after my refresh, it suddenly started showing the new value.
Mm-hmm.
Yeah, so that I saw it as part of Flipkart itself during the sale itself. So I probably guess these systems, right? They still so it depends on how much of so that, see, just think that there was a replication lag which really happened during that time. So probably I think it is like it depends on systems how they are designed, and for which one you can still tolerate replication lag. Like, yeah, this pricing can still be tolerated, right? So a user can, but it may not be a very good user experience. But one of the case can happen, right? Like mine happened, but I still understood that okay, this happened because of replication lag. So now I just refreshed it, then the new value came back. But yeah, but for say for, I would tell, for transaction like ordering and all, I probably guess replication lag should not be that. There should be a single streaming which should happen. I'm not sure how systems handle behind the scene, but probably they would be reading every data from the master. But yeah, I think so. The recent transaction may go to the master. but subsequent transactions, right, may go on to the replicas to read the data thinking that by that time the replication would have happened. Saying, so in this scenario, right, so wait for 1 minute, and then you wait for 1 minute, and then you subsequently, so all that request which happened would go here. But subsequently, after a minute, I send another request. Then I would redirect it to one of the replicas which has the latest data. So what I would then I need to maintain somewhere saying that okay, this replica has the latest data, this has the latest data, which is in sync with the master. Then I start routing the request to that particular replica. So subsequently, other replicas would start coming up with the latest value. So then I would, yeah, it's actually, yeah, so it becomes very complex as we go in. I probably guess that is where your consensus algorithm starts coming into play. Basically, how do you maintain all these? Then your raft consensus algorithm starts coming into play. So that should be a consensus between the leader and the replica, right? Without that, it's not going to happen. Whether the leader is having the latest data or the replica is having the latest data. So how do you figure it out? So how does the leader know that one of the replica has the latest data, so that he can send back the response? So all these, I think, as part of the subsequent classes, I would be speaking about the consensus algorithm. Then we may get to know how replication is done. So internally, how the system tries to identify that, yeah, one of the replica is having the latest data, and I can go there.
Okay, awesome.
Yeah, any questions?
No,
Tarun,
go ahead.
yeah.
Yes, perfect.
So then you have monotonic rate. It is possible. So monotonic rate is nothing but monotonically you keep on increasing. There's no backward in time. That's what you always move it forward in time. So the user should not see the data in backward in time. He should always see, say that say that for X minute he has sent a request, then subsequent requests should see X plus 1 data only. It should not see X minus 1 data or X data. So that's what is basically a monotonic read. So this monotonic read, all these comes as part of your linearization, and it's part of casual consistency. This can see, so how do you, so this can happen if the user makes several different reads from different replicas. So that's the one problem. And the other thing is you never go back in time. So then redirect the user to the replica based on the hash value. So basically you tell that, okay, now if this is the user, then you always redirect to a particular replica for that user which has the latest data. What if the replica goes 10? Then pick the replica which has the latest data from the latest replica. That's it. That's what you do. So it's very simple. If you see the diagram, right? So you write it into the leader, then it gets replicated. By that time, a user sends a request. You read that from any of the replica, and then you send back. Subsequent, you always move in forward in time. So when a request, so after the insertion has happened in this replica, right? Then when a request comes in, right? So you read it from this replica and you move forward. So subsequently, so then after this has happened, right? Say that replication happens only here. So once this request, you start sending all the, so once it has got the latest data, then subsequently in any point of time, right? This would have the latest data. So you always send the request to this, or you send it to the leader. Once a replica is done in the replication 2, right, then subsequent read can go here also. Then subsequent read can go here also. It doesn't matter. So it is that. So the point is that this, when you send a request, right, the request should never read something from here. That's the only point in this, in the monotonic read. So you always move in forward in time, and so that the user does not seize the older data. That's the main thing. So one way is to achieve achieve monotonic read is to make sure that the user always makes a read from the same replica. So as I told, once it is read from here, you keep on reading it from the same replica because it has the latest data. So that's how you achieve this replication. So this is more of a straightforward if you try to implement this than the previous one. So one thing is monotonic read, right? Is a it guarantees that this kind of anonymity will not happen. That is, it will not go back in time to read the data, and it is less guarantee than the stronger consistency. So one thing is that it does not give you very strong consistency, but but it gives you a strong guarantee than the eventual consistency, because when you compare to the previous one, right, this one is much more guaranteed because at least you know that it always, you send the request always to the latest replica which has the latest data, and you always move in forward in time, then just randomly sending the request to a different replica which does not have the latest data. That is what it means, a strong guarantee than an eventual consistency. So any question here? So this monotonic read, right, can be seen as part of a casual, actually casual consistency. It comes as part of a casual consistency. Monotonic read, monotonic write. There's something called monotonic write also. And yeah, so your read your own writes, write follows read. All these are part of your casual consistency. And if you see the names itself, right, it's more like to avoid your replication lags and all. So using casual consistency, you can avoid some of your replication lags also, and it gives you, yeah, that's why even if you see in the MongoDB documentation, it tells more of a casual consistency. It's more of configurational, but it tells it's more than eventual consistency, because it somehow gives you a guarantee that you will always read at least the latest data from any one of the replicas.
So Manoj, two strategies we have discussed so far.
Yeah.
One is having some time delay, for example, 1 minute, for which within which you will read from the master instance, right?
Yeah, so
Later,
one is always reading it from the leader itself. Say that, so example, like your social media profile, you make change. It's more of it's not going to be a lot of people going to look into your profile, right? Then reading your post. Post is the one which is highly read than you're looking into your profile. Say that 100 times your post is seen, I would tell only 10% of that people will look into your profile.
right, right.
Right? So that is why we tell that. So whenever you make changes to your profile, it makes sure that that user, at least the user who has made the change, at least sees what change he has done. So we tell that go every time he may. So because the client knows that he has made a change to the profile, right?
Yeah, yeah.
So the client has to be very smart. So
Right, right.
it redirects it to the leader itself, because in the response it knows that this is the leader which has your latest data that has to be sent. So then subsequent requests can be sent there itself.
Right.
So that's why we tell. So the other way of achieving it is just push all the requests which is coming for that particular change to the leader, and then after 1 minute, then subsequently push it to the this thing. Say you have made a change, and how do you know that the other clients would be knowing it? So one thing is that so because if some of the request goes to the other replica, but you have made a change, then one of the replica got the latest change, then subsequently you know that there is a stale data which has happened. Then by looking at the timestamp or something, then you can fall back and make it to always go to the leader, and then subsequently after a minute, then you start pushing it to the replicas, because by that time it would have replicated.
Right.
Yeah, so the other thing is making the client to remember any request that you follow, send it to the leader, or um, to the replica which has the latest data of the change.
Correct.
There are three things within one thing here.
Okay.
So how do you achieve read your own rights? And next is your monotonic read. Monotonic read is more like, yeah, you do straightforward. You always move forward in time, and you never go back in time. And so redirect the users to the replica that has the latest change always. And that's it.
Right. So you look out for multiple instances, and in
Yeah.
case there are differences in the data, what do you do?
No, so yeah, so that is what. So if you see, right, so that is where, right, you. So this is more like to understand the problem, but when you actually go on to implementation, right? So that is where you have. This is more of a single leader replication, but you have multi-leader, leaderless replications and all, right? Where it tries to handle your Cassandra, right? So when you do a write, you have a quorum, right? Saying that at least 3 writes should go, right? Or 4 writes should be done on the
Okay.
and then respond back, right? So now you take that, you read one of so when you're trying to read, you don't read it from one replica, right? You try to read across the replica that got, and then trying to compare the time. So that's more of an application side, and you try.
Okay.
That's how you solve that problem. So this is more of a single leader. This is more of a single leader trying to solve the replication lag. So I think in subsequent classes we can see about multi-leader and leaderless how replication lags can be solved. And yeah, so how your raft algorithms, raft consensus algorithm also comes into picture, because when you go into all these multi-leader, leaderless, right, there has to be some consensus between the replications, right?
Right. Right.
So yeah, that's where all these starts coming in.
Yes. Or a simple way to handle that conflicts could be return the result which is common across most of the instances, right? Or have a majority, or you can have, say, some threshold that until unless two replicas have the same data, you will return that value only if there are more than
Yeah,
one.
that's right. Yeah. So
Yes,
how do we know that? How do we know that system has got, say that a request, a user sends a request to the leader.
Yeah.
Okay. So then he responds back. Okay. By there would be by this getting responded, and subsequently within this time, right, when this is happening, and there is a request which is coming in, right? How does the system know that, okay, this has got replicated or not? Then that's where you need to have like zookeeper or someone who keeps track of all these. Okay, this system got replicated with the new data, and it's maintaining the newest data. So that is when, as the request comes, then you start, based on that only you will be able to route the request to that particular replica which has the latest data. If not, yeah, we are not going to be able to manage that, because until you tell the system where which replica has the latest data, no system is going to be found. No system will be able to find on its own, right? So that's why you try mitigating a problem, then you come up with a different problem altogether. So now, how do we make like a zookeeper system to have the latest data? Then yeah, that's also something that we need to think about. Yeah. So one thing I would always tell is that in a distributed system, things become very complex. As you try solving one problem, then you come up with another problem. So you should always have a trade-off. Okay, so saying that, okay, this is fine, where we can trade off with this. And if it is something that it is business critical and we cannot solve, then we need to trade off something else and come up with a different approach.
Nice. Go ahead.
Yeah, so the last one is consent prefix read. So it's, the problem is like seeing in the future. Say, yeah, this is something that I wrote. Say that there are two people speaking. So one is saying, how far can you see in the future? And the other person say, Mr. Manoj says, as 10 minutes as usual. So now consider that so now another person is also looking into that. So there is a group chat happening, and one person sends a message, and another person responds. Another person is looking into that group chat, is also a part of that group chat, right? So, but what happens is this person, right, this Suresh, right, actually sees this person message before he could see this message. So this comes second, and this comes first. So that is what that's the actual problem. So how do you solve these problems? That's because actually the replication, because of the replication only. So because one of the replication would have taken, say that this took a shorter replication time to replicate, when this took longer replication time. So that's what I have shown in the diagram, saying that T1 user and so both of them are trying to write it into leader partition. But so one of them, right? So the T3, right? So this is the T3 user who is actually seeing the seeing T2 users time. I mean message before even T1's time. So that is what. So if you see this as a time, right? So this replication took a shorter time, and it came, and he was seeing, I will send it in 5 minutes. That's this time he's seeing first. But this replication, right, it took longer, and that is why he's seeing when can I see the data. So this comes after. So how do you solve these type of problems? Yes, one simple way is using timestamp from the center. You just sort it and then send it. That's the only way you can solve it. This, yeah. So why does these problems occur? This is because of partitioning. So one way you can solve this is send all the data to one partition. That is how you can solve it. If not, then you need to basically sort it by timestamp and then send it to the system. So basically, you need to wait. Is there a message? Basically, you need to have a wait every time. But if that's you have a problem with that, then the only way is you send all the. If it is a group chat, then you have single channel, and you write it into one partitioning. You create a group partition, and then that entire chat, right, goes through that partition. Then you will be able to solve this problem. If not, it's very difficult, because if you randomly write about different partitioning and you're trying to have a group chat or a system that you want to actually maintain the order in which the message is sent, then it's going to be very super difficult to maintain in a distributed system. Yeah, that's it from my end for this replication lag. So in the subsequent class, we'll have a look at how do you solve these replication. So how do you solution for this? There are different solutions of these are some of the solutions, but for multi-leader or leaderless, there would be again lags. How do you solve all these? So any question here?
There are also some replication types like one-way replication, two-way replication. So
I'm not aware of that, but you can give me an hint. What is one-way replication? And
so
one-way
one-way
replication is basically from the statement. I think that you
primary
replicate
data,
from one
yeah.
system to another system and then leave it, right?
Yes, absolutely.
So one thing is, right, like your CQRS, right, which is basically one-way replication, because you write it into one system, right, and then do a replicate to a read system, right? So you send all the, so subsequent all the writes always come here to this system, but it gets replicated to a read system. All the reads come here only. CQRS pattern, right? That is more like one-way replication. You
Right,
do
right.
this way, and I probably guess most of the time it is from the leader. It happens because the leader is responsible for maintaining the latest data. Uh, so even in Cassandra, right, which follows, I think it follows the leaderless protocol, right?
Yes.
Right. So there also even one. It is always the leader who takes the right, and from that is the leader who sends the data. So the request goes and writes that, then the leader sends out acknowledgement, and then yeah, subsequent writes happen, and that's a commit, and then that's when it responds back. So normally I think in any database system, right, it's the leader who's responsible for maintaining the latest data. If not, right, yeah, you cannot even solve that problem. I really don't know how to solve that problem. Writing data as you like.
Great.
Yeah. So what is two-way? I'm not aware of that. Way.
Two-way data replication is in which both the primary and secondary databases are actively involved in replicating data.
Ah, okay.
Right. So I think this is mostly similar to the consensus based replication where you may have different updates in different systems and then you decide which one to copy.
Yeah. So but yeah. So now, say for example, say that you have two different systems. One is sending data, but say that this has T1 and this has T2 timestamp, right? And this is latest, and this is the old data, right? But how does this replica, right? Replica knows that this system is out of date. There should be some system in between, right? Managing these two, right? But
Yeah,
I'm
so
not.
the two systems they will decide between
Okay.
each other which one is the latest and what to update.
Okay. So they send data across between them, and they decide which
Yes,
one
yes.
has the latest data, and they overwrite the existing data. Okay.
Correct, correct.
But
So
this
some
becomes
scenario
very
could
complicated, right? Because say writes happen here, and then writes happen here also. Then
yes.
kudos, because say that first time a user one, right, sends a request. First it writes here, even before it could get replicated. Subsequently, users the same user, right?
Right.
Same
Yeah,
user
absolutely.
sends here, then I'm not sure because by that time, right, the data would be something totally different here, right? You would be seeing a different data, right, altogether. And because this change would have got reflected, but he would send it here to change the data, but it would be completely different. And by the time it is trying to replicate, and there'll be a conflict happening here, right?
Yes, yes, absolutely. Right. Like in our code in the Git code repository or any version control, you may be modifying the local copies and then you
Ah, yeah.
sync, right? Or in the Google Doc or any cloud based document editing and collaboration tool, where you may have a local copy, offline copy, and a cloud copy. And then when you sync, these two copies could have been modified by different users at different times, and you need
Yeah.
to sync, replicate between them.
Yeah, so one thing so GitHub, right, uses Fino, right? It's called Fino. They use a system called Fino to overcome this replication lag. I think I can even take a take a class on how did they mitigate. So there is an engineering blog where they have written about it.
Okay.
We can even speak about it. How did they solve it? So just to give a notice. So when there is lot of say that there is a lot of code changes, what they do is they break down into smaller pieces of pieces, and they start applying that changes very rapidly. By the time there's a request coming in, they see only those changes, and subsequently they take that and they start going forward. That is how they use. That's where because I think they use Postgres or MySQL. I'm not sure. I don't remember, but which was not actually supported. So they wrote their own replication system called Frango.
Okay.
Fringo.
Uh-huh.
Frino. They call it as Frino, I think. So that's yeah. We can. It's a very interesting problem. How GitHub engineers smartly solve that problem. Yeah, I think that would give an insight how yeah in future if you really want to design a system and you come across this, then yeah, I think GitHub problem can help you in giving you an insight to solve that problem.
Sure.
Anything? If no, yeah, if there's no question, then I take it as
Sure, sure. Yeah. Now, no, thanks.
yeah, yeah. I'll share this. Yeah, I probably guess I draw this diagram using Whimsical. I'll just share the Whimsical link so that yeah, you can have a look of this. It's the same thing that I spoke in words. I just drew it as a diagram so that in future if you try to look into it, it becomes very easy to have an easy understanding by looking at the picture.
Great. Great. Thank you.
Yeah, thanks.
Thanks,
You.
Manoj, for
Thank
the
you. Yeah,
presentation. Thanks, Tarun, for hosting.
yeah. Thanks,
Great
Suresh.
night.
Yeah, thanks so much. Yeah, do yeah, ping us if you still have any questions or anything. You can still ping on the WhatsApp. I would try helping you out.
Sure, Manoj.
Great.
Thanks.
Great. Awesome. See you. Bye. Have a
Yeah,
nice
thank you.
evening.
Thank you, Karan. Thank you, guys. Bye.